Swayam Prabha. Digital India. Educated India.
Namaskar. So, in the last class we started our discussion on the topic called network stability, and we will continue our discussion today about the network stability, and also we will discuss about the network synthesis. So, let us start the discussion of today's lecture. So, in the last class we discussed about the network stability. So, what we discussed that the circuit is stable if its impulse response, that is Ht, is bounded as time t tends to infinity. So, that means that impulse response will converge to a finite value when time t tends to infinity, and it will be unstable if Ht grows without bound as t tends to infinity. So, we also discussed that in mathematical term we can write it as limit t tends to infinity Ht is finite. Now, if Hs is the Laplace transform of Ht, we discussed that it can be represented as Ns by ds in the Laplace transform domain. The impulse response Ht, Hs, that is the Laplace transform of the impulse response Ht, must meet the following requirement in order to circuit to be stable. So, what was those requirements? One requirement which we discussed was the degree of Ns must be less than the degree of ds, that is degree of numerator expression should be less than the degree of expression in denominator. Next requirement is that all poles of Hs must have negative real part. All poles means all roots of the denominator expression must have negative real part. Now, we also discussed that the circuits which are made up of passive elements, that is RLC elements, and independent sources will not be unstable, because if we say that these can be unstable, that means that there would be some branch currents or voltages which would grow indefinitely with source is set to 0, which generally is not the case when we analyze the RLC circuits. So, let us verify our saying that the passive elements and independent sources elements network will not be unstable. So, let us see the example, that is what we also discussed in the previous lecture, that if it is a series RLC circuit, we can say that V naught by Vs can be represented as 1 upon Lc divided by S square plus R by L S plus 1 by Lc, and we also discussed that the denominator component, that is the denominator expression, that is S square plus R by L S plus 1 by Lc is equal to 0 is already we have discussed when we were discussing about the series RLC circuit. So, this would be the characteristic equation which we have already discussed in the past. So, we can say that the poles of the denominator expression will have, the roots of the denominator expression will have value P12 is equal to minus alpha plus minus root of alpha square minus omega naught square, and we also stabilize that alpha is equal to R by 2L and omega naught is equal to 1 by root Lc. Now, if you see that the RLC is greater than 0, when if this is the condition, the two poles will always right in the left half of plane. So, that means that in the network which contains R, L and C components will not be unstable, because the poles which we get from the given transfer function of the circuit will have always negative real part. The critical condition which we discussed was that when R is equal to 0, the damping coefficient would be 0. In that case, the circuit will become oscillatory. Now, there are certain circuits like active circuits or the passive circuits which contains the control sources which can supply energy, and that is why they can be unstable. The oscillator is another example of such circuits which is designed to be unstable, because it will not die out to some constant value when the time t tends to infinity. So, when you design the oscillator, the transfer function of oscillator can be given as Hs is equal to Ns divided by S square plus omega naught square, which can be represented as Ns divided by S plus j omega naught into S minus j omega naught. So, you will see that the poles of this particular transfer functions are lying at the imaginary axis. So, the poles are minus j omega naught and plus j omega naught. So, when you have poles lying on the imaginary axis, that means that the circuit is oscillatory. The output which you will get in this case is sinusoidal. So, when you have this kind of situation, then you will say that the circuit is oscillatory. Now, let us take one example so that we can understand the concept. We need to determine the value of k for which the circuit which is given in the figure is stable. So, now here you see that you have one energy storage component, that is capacitor. 1 by Sc is the value of the capacitance in S domain, and we have two resistances. We have one dependent voltage source which depends upon the current flowing in this loop. So, we need to find out the value of k for which this particular figure will be stable. So, what we have to do? We have to first use the mesh analysis and write the equations for these two loops. For first loop, what you can write? Vi is nothing but R plus 1 by Sc, both are in this particular loop, into I1. So, that is the current which is flowing in these two components, minus I2 upon Sc, because for in the capacitor I1 is flowing in this direction while I2 is flowing in the opposite direction. So, your value for Vi would be R plus 1 by Sc into I1 minus I2 by Sc. So, this is the first equation which you got from loop 1. Similarly, for loop 2, what you will write? Since I2 is flowing in the opposite direction starting from minus to plus, so you will get the dependent voltage source value as minus k I1, then plus R plus Sc, R plus 1 by Sc multiplied by I2, because I2 is flowing in these two. So, then you get R plus 1 by Sc into I2 minus I1 by Sc, because I1 and I2 are opposite in this capacitor component. So, when you rearrange, you will get another equation which is in the form of I1 and I2. So, now you have these two equations. If you represent them in matrix form, how you will write? You can write these two equations as V1 is there in the left hand side, here the value is 0. So, you will write V1 0, then you will arrange the components. So, corresponding to I1 we have R plus 1 by Sc, and for I2 it is minus 1 by Sc, and similarly here I1 is plus I1 component is k plus 1 by Sc with minus sign, plus R plus 1 by Sc for I2. So, when you compile the matrix, you will see that if you want to find out the characteristic equation of this particular circuit, governing characteristic equation, then what you have to do, you have to just find out the determinant of the matrix which we have just compiled. So, what would be the value of determinant? So, determinant, let us say it is delta. So, we will say that the value of determinant is nothing but r plus 1 by s c square minus, because minus minus will become plus, and then you will see another minus for the determinant calculation, and then multiply by 1 by s c in this particular term, you will get minus k by s c minus 1 upon s square c square. So, when you rearrange the term, you will see the value of determinant is nothing but s r square c plus 2 r minus k. Now, if you put the value of delta equal to 0, that would be nothing but the characteristic equation. Then what you will get? You will get the value of single pole, because here this is the numerator component is only containing the degree of s is 1. So, you will have only one single pole. So, the value of pole P would be k minus 2 r upon r square c. So, now if you see this particular value of pole P, you will say that the pole would be negative when k is less than 2 r. So, what we can say that the circuit will be stable when k is less than 2 r, otherwise for k greater than 2 r the circuit would be unstable. So, this you can verify you can find out the value of k for which your circuit will be stable. Now, let us talk about another concept called network synthesis. So, what is network synthesis? Network synthesis is the process of obtaining an appropriate network for a given transfer function. Now, this network synthesis is just opposite to our network analysis, where we get the circuit and we try to find out the transfer function of the given circuit. So, network synthesis is easier to carry out in S domain than in the time domain. So, when we differentiate between network synthesis and network analysis, we can say that in network analysis we find the transfer function of a given network, while in case of network synthesis we reverse the approach. That means, we are required to find a suitable network for a given transfer function. So, in case of network synthesis, what we will do? We will get one transfer function, and from that we will try to find out the suitable network which satisfy the transfer function. Now, in network synthesis there may be many different answers to, or possibly no answers, because there may be many circuits that can be used to represent the same transfer function. So, we need to find out the most suitable answer for given transfer function. While in network analysis the things are opposite, means there will be only one answer, means for network analysis we will always get one single transfer function, but in case of network synthesis one transfer function can represent multiple circuits. So, let us understand these concepts with the help of examples, because that would be easier to understand the synthesis aspect of the circuit. Let us see that there is one transfer function given as V naught s upon V I s is equal to 10 upon s square plus 3s plus 10. Now, let us say that this is the circuit where L and C are presented and C is in parallel with R, and the ratio, that is V naught by V I, is nothing but the ratio between voltage across resistance R divided by input voltage. So, now we have got this transfer function and we have the idea that this would be the circuit. What we have to do, since we have three unknowns here R, L and C, we will fix one value, that is R. Why we will fix that value? We will see when we will progress with the solution, that why we are fixing value of R, and finding out the value of C. So, we will take two cases where R is 5 ohm and R is 1 ohm, and we will try to find out the value of L and C. Now, first what we have to do, we have to find out the S domain equivalent of the circuit. So, when you create the S domain equivalent of the circuit, it will look like as shown in the figure. So, this is VIS, that is the input voltage, V naught S is across the resistance R, and then the inductor will become SL and capacitance will be 1 by SC. Now, the capacitor and the resistor are in parallel, and this voltage would be applied across both the components because both are in parallel. So, we can find out the equivalent impedance of this particular parallel combination. So, what the value we get since R is in parallel with 1 by SC, when we solve that we will get the equivalent impedance in S domain, that is nothing but R upon 1 plus SRC. Now, we can utilize the voltage division principle, since this V naught is also across the capacitance. So, basically the parallel combination of capacitance and resistance will have the voltage V naught S across them. So, we can utilize the voltage division principle and find out the value of V naught in terms of Vi. So, what we can write, V naught is nothing but the value, that is R into R divided by 1 plus SRC divided by the SL, that is in series with the parallel combination of the R and C. So, in denominator we will get SL plus R divided by 1 plus SRC into Vi. Now, the transfer function which we get is V naught by Vi, and when we will rearrange, we can say that it is equal to 1 upon L C divided by S square plus S upon R C plus 1 by L C. Now, if you see the transfer function, that is 10 upon S square plus 3S plus 10. So, that should be equal to 10 upon S square plus 3S plus 10. So, if you compare both of them, you will get 1 by L C equal to 10 and 1 by R C equal to 3. So, these are the two values which we will get when we compare the transfer functions. Now, as we have only two equations and 3 unknowns, we cannot find out the solution until unless we fix one quantity. So, that is what we discussed in the last slide, that we need to fix at least one, so that we can get the answer. So, what we had in our question is, let us fix value as R is equal to 5 ohm. So, when you put R is equal to 5 ohm, the value of C you will get is 66.67 millifarad and L is 1.5 Henry. Now, when you have R is equal to 1 ohm, then C will be 0.333 farad and L is equal to 0.3 Henry. Now, making R is equal to 1 ohm generally is said that it is normalizing the design, because you are fixing R as 1 ohm means you are normalizing the design of the circuit. So, with this you can find out the value of unknowns, that is L and C, but you have to fix at least one component. So, in this case we fixed the value of resistance R. Now, let us take another example. In this case the transfer function is given and we need to find out the value of L and C again when the value of R is given, that is 2 ohm. So, first task which is required is that convert the given circuit into S domain. So, here you see that R, L and C both all of 3 are in series. So, the equivalent S domain of the given circuit would be C will be replaced by 1 by SC, L in place of L we will see SL, and V naught T will become V naught S in S domain, R will remain same, and Vi at any time t will become Vi S. So, what we have to do next? Now, we have to write the loop equation and represent the voltage across R as part of Vi, so that we get the transfer function. So, when we write the loop equation and rearrange the voltage across R as in terms of Vi, we can write V naught by Vi is nothing but R, because voltage V naught is across R divided by all three series components. So, we can write 1 upon SC plus SL plus R. When we rearrange, you can simply write R by L S divided by S square plus R by L S plus 1 by L C. Now, you have got this transfer function based on the unknowns which you have in the circuit. The transfer function which is given to us is 4s upon S square plus 4s plus 20. So, if you compare both of them, you can simply say that R by L is nothing but equal to 4 and 1 by L C is equal to 20. So, here again you have two equations, but you have three unknowns. So, we fix value of R as 2 ohm. So, when you fix the value of R as 2 ohm, you can simply get the value of L as 0.5 Henry and capacitance C as 0.1 farad. So, basically with this particular process, you can easily find out the values of the unknowns. So, in this case the unknowns were C and L, and we fix the value of R. So, this is how you progress when you are asked to do the network synthesis. So, with this we can close our today's session. So, in this session we discussed about the network synthesis in detail, and also carried out our discussion on network stability, and particularly in this week we discussed about the application of Laplace transform in various circuit analysis. So, we close this week's session with this note that we will discuss the two port network in the next week. Thank you.